Good morning everybody. Last class we looked at the non-normality of thermoacoustic system. We found that this operator here is actually non-normal and which results in this non-orthogonal eigenmodes, and we saw that if you have a system where the eigenmodes are decaying, even as they decay you can end up having growth in short term. This is called transient growth, and then we saw that we saw with both with parallelogram law and triangle law, and then we said that if the transient growth is high enough then nonlinear instabilities will become important, and then you can have nonlinear instabilities. So this is where we stop, and then we are going to look at the Recay tube model. So one way you can look at it is from the dynamic system point of view. They think of a basin boundary, so you can think of this green potato shaped object as like a basin boundary, and you can see along some direction. For example, if you want to go along this axis, it takes a large kick to get out and to be outside the basin boundary. So anything outside this basin boundary will eventually come to this curve which is symbolic of the limit cycle. But if you are maybe inside, just inside the dimple, which may not be very far from the origin at all, you need just a very small disturbance to get out into this area of dimple, and then you can really go out to the limit cycle. We will look more carefully at how it does. So this has something to do with the topology of the phase space or geometry of the phase space and so on. So that is a cartoon which illustrates these things. So now we are looking at the Recay tube model, which we already derived in class, a simple model, and it just needs a representation of the acoustic field and some kind of expression for the heat release rate. So we wrote the momentum and energy equations, and then we did a model expansion. We already worked this out in the class, and we are attempting to get time domain solution because we are interested in seeing the transients, and time domain is a very good way to look at the transients, and we need a model for the heat release rate. So we need to express the heat release rate fluctuations as a function of velocity, but then there may be delays in the system. In this case the delays from the boundary layer, thermal and momentum boundary layer of the wire, so there will be a delay tau, and so we say that the heat release is actually a function of the velocity fluctuation at an earlier time, that's t minus tau. Now you do not have to do this, you can actually use CFD to solve the flow around the cylinder and calculate the heat release rate from those calculations, which is quite involved, but I wanted to keep the problem as a toy problem, very simple problem. That is the reason I take this approach, and this is the correlation given by Haeckel. We did this, in fact we even linearized this in the class and derived a linearized operator and so on. And I said that this law enables us to get nonlinear terms important when u prime over u bar is of the order of 1/3, and this Haeckel says is what she sees in experiment, debatable, but this is what she says, and then we can get something of the form like an evolution equation, as what people say in dynamical systems theory, a dk by dt plus some operator, linear operator acting on chi, plus a nonlinear operator acting on nonlinear function of chi is 0. So the linearized system will have only the first two terms. So and if there is nonlinearities, you will have of course a nonlinear function. This kind of representation is you know what it is called, state space representation in dynamical system theory, also in control theory. So we will look at some examples. So we will run a calculation with no damping because there are a lot of theories and debates and controversies about damping, so we just stay away. We look at the undamped system. So I have given the parameters at the bottom of the screen. You start with a small excitation and you see some kind of growth in velocity followed by decay. Okay, so this is like you can actually, if you are in a subcritical zone and you make a snap the fingers near a Recay tube, you can actually hear this. Now if you jack up the initial condition just a touch more, you actually get a different asymptotic state. You are not actually going to a fixed point or not going to equilibrium or die down, but here it is actually going to some kind of limit cycle. Now if you, so this is subcritical transition to instability, which, or combustion instability people call it, what is the name? Triggering instability. And if you look at the energy, you can see that the, so energy is a measure of how much fluctuation is there, energy is a measure. Now you see that, so this is the acoustic energy that I used, scaled. So scaled, no this is not scaled, this is the acoustic energy, and you see the linear evolution, it goes up, and then we are looking at a subcritical system, so eventually everything has to die down to 0, and but the non-linear system actually takes off and goes to a high value where limit cycle is reached. And it is interesting to look at the phase. We know that the system does not have damping, so as you reach the instability, what should be the value of phase as you reach limit cycle? Yeah, why?
Because there is no net power.
Right. So once you are in limit cycle, there is no damping, so there is no loss of acoustic energy, and limit cycle means you are staying there, you have a constant energy, so you do not need any driving also, there is nothing going out, nothing coming in, and you already reach some level and you are just staying there. So you can actually see, though our model did not have damping, we see a limit cycle in the absence of damping, and we can also see that the phase is evolving to something like 90 degree and so on. Okay, so is this clear?
In that energy time diagram,
yes,
those are two different systems, non-linear.
It's the same system, but I am running a non-linear, there is a non-linear system, I am linearizing the system and get a linearized operator, and I am evolving that. So it is the same system, but you are looking at it as a fully non-linear system or a linearized version of the same system. So they are, in effect, there are two systems, because one is a non-linear system, one is a linear system, but the basic thermoacoustic system, we have a non-linear model, and what happens if you linearize it? So in that sense they are same.
Shouldn't non-linearities come in after some time, like after an amplitude, like in this beginning, or
so in the beginning the amplitudes are small, so the non-linear thing will essentially look like linear, that is what is happening. So
oh, it's sum of non-linear plus.
yeah, the non-linear evolution is the, you take the non-linear evolution and integrate forward and see what happens. So it has everything, a non-linear simulation has linear and non-linear. Oh, you are talking about subtracting one from the other, no, that is not what is done. Okay, very good point. So so you can see here at low amplitude the trend of the non-linear simulation is very similar to linear, so that means the non-linear terms are kind of they are getting significant as the time progresses, as the amplitude increases. So you are absolutely right. Any other question? So we will run a model including damping. We saw a model for damping. What was the model that we used? No, Ento model is the model for heat release rate. We use a specific type of model. Which was like modal damping, it was given by Matt View. So of this form, for each mode is damped this way, and this is used by Matt View in his thesis on Ricky tube, and I think originally it is proposed by Stirling and Zukowski in 1991. So we use that, and we see that same kind of transient growth followed by decay can be seen, and so you have a small initial condition, you have growth and decay, but a slightly different initial condition leads it to like a limit cycle. So you can see that triggering is occurring even if you choose some model of damping, but what model of damping to choose is, I am sure it is very critical, but this is a model problem, so I am putting in some model which is available. Okay. So even the energy evolution does look very similar. So you can see the linear evolution, it has to die down because we are looking at by definition a subcritical system, all eigenvectors are decaying because all eigenvalues show negative growth rate, so it is dying, but the nonlinear system actually kind of follows the linear system for some time, but then eventually it goes to a limit cycle. So you do not necessarily have to get curves of this shape, but the linear simulation, if the eigenvectors are decaying, has to die, and the nonlinear one. So the other important thing is, if you run the nonlinear simulation at low amplitude, that will look very identical to the linear simulation, okay, because those nonlinearities which make the system take it out of the basin of attraction has not really kicked in.
So once the transient growth has gone over a limit, then it will always go to nonlinearity.
Yeah, so see, so it's you have to watch. Let me go back to the picture here. So you have a basin of attraction, either you are out or in, like Bush says, either you are with them or with me. So either you are inside the basin of attraction or outside the basin of attraction, but the linear mechanisms does cause some growth. So it is not like the linear mechanism will make you jump out of the basin of attraction, no, either you are out of the basin of attraction or inside the basin of attraction. But what the linear thing does is it flattens this, or it smashes some part of the basin of attraction, because why is a smash? Because the linear mechanisms, see, had it been a sphere, it does not matter where you start with, but because if you linearize the problem and look at it, you can actually, let us look at a 2D case. It may be a highly distorted thing. So this distance may be very large, but this is very small. So if you just so you start off with this, and you may be able to somehow grow here or something, or get out that way. So what this does is to, so because of the linear mechanisms causing growth, the level at which nonlinearities become important is different along different directions. So along some directions, for example in this punched potato, you may need only a small amplitude to be out of the basin of attraction. So once you are out of the basin of attraction, nonlinearities has to be taken into account, but even so, along the from here, linear mechanisms are itself still operating, and it is causing you to grow. So you have to view it in a little imaginative and careful way. So we cannot say that the linear mechanisms are making you go out of the basin of attraction. You are always out of the basin of attraction if you are outside. If you are in, you are always in, you cannot get in. But if non-normality is there, the basin of attraction would not look uniform because of this linear mechanisms causing growth. Is that clear? That is one way to look at it. The other ways, as you said, the non-normalities can cause growth, therefore and you can have very significant growth, and therefore it may grow to values, you may start with very small amplitude 1% or 0.1%, but the linear mechanisms itself may make it grow to 10% or 20%. So just because you started out with small, even with linear mechanisms we can get very high. So then but at those amplitudes linearization will not be valid along those directions. So you have to be very careful in figuring out at what amplitudes linearization is valid. So basically non-normality reduces the amplitudes at which linearization is valid, or even at small amplitudes you can have linearization fail and non-linearities being important.
And in different directions you get different.
Right, and the you can in a normal system can change direction in which it evolves. Okay, I mean you can evolve in any direction anyway, but as it changes direction you can have growth. This is clear. Thank you for asking this. Any other questions?
What determines the direction of this?
Yeah, that is our next part, which is the best direction. That's what I'm going to talk about. So it will take half an hour to address, and that's what I don't have a one word answer. Any other questions? So before I go, the whole idea came to me because I made a combustor in 90s, and it had it was always it was a tunable pulse combustor. It's still there in our lab, and I think maybe some of you have seen it. It actually works from very low frequency, from 70-80 hertz to 600-700 hertz, in that range, and but you could never get it to work straight away in fundamental mode. But the student who was working, his name is Ram Narayanan Balachandran, he is now a professor in University College London. He had some kind of magic with which he could get it to work. So he would be working it under third mode 200 and something hertz or something, and it's a bluff body combustor, so the position of the bluff body is very important, and with a sleight of hand he will change the position of the bluff body, and this mode will die and the other mode will come up. So you can see here this is the evolution of the velocity. It is actually a decaying system here, some mode is dying. Here in this case some low frequency mode is dying and then a high frequency mode came. What he had was the opposite thing, and if you see the projection on the modes, you can see that the first mode is dying, but as it is dying it is giving energy to this and this. So this is a subcritical system, eigenvectors all decay, and then this is about dead, but then these guys are giving energy back to it, it is going up like our Bollywood movies. The hero was kind when he was young and he helped everybody else, but then he was in a disaster and he was all set to die, and then somebody comes and bails him out or something. So some kind of thing is happening here, but you do not have to look at it that way, but you see. So a system, if it is initially decaying, it does not mean it will continue to decay and can come back up, that is non-linearities are there. Okay. I thought it was interesting to mention this. Now the question is, as what he asked, how can you quantify energy growth? Vikram, right? Yeah. So there are two things, only the direction and how much it is growing, right, and the growth definitely should depend on the direction, as you rightly pointed out, because if I showed the example last time that if you are exciting things around the eigenvector, then what happens, will there be transient growth? There cannot be a transient growth, because by definition the eigenvector is decaying, and if you do not have contribution along other eigenvectors you just continue to decay. So from this example itself it is abundantly clear that you have to, I mean the whole thing is the growth is directional dependent. If you are along some direction you may have transient growth, some other direction you may not have transient growth at all. So the answer is to quantify you have to have a measure or a norm, and when I heard this first, this was my expression, because I am not a mathematician or a physicist and I can measure quantities, but I did not understand what was a norm. So I had to experiment. People who do experiments sometimes get thoroughly discouraged when they hear fancy jargon, but soon I found out that there is nothing to worry about, because I will explain to you, because I understood pretty soon what it was, although the mathematicians scared me with the talk of norm and measure and so on. I understood that first I thought measure was a complicated thing, but then I understood that anything to measure you need a measure, and it's just like English word, it's just that they write lemmas and theorems and throw you out. So 2 norm of a vector is nothing but its length in the Euclidean space. So we have a pencil or pen and I can measure the length. I do not call it 2 norm or measure or something like that, but all that needed is I have 3 coordinates, and the x1 squared plus x2 squared plus x3 or x squared plus y squared plus z squared is the length. That's all. It's very simple, right? So so this is geometric space or normal space, Euclidean geometry. So you can have a 3-dimensional vector a xi plus yj plus zk, and the length is x squared plus y squared plus z squared. So we want to extend this to something which has many components, let us say not just ijk but 100 directions or 1000 directions. No, I can't imagine 100 directions and 1000 directions, I can imagine 1, 2 and 3, but as long as I do not have to draw, I could accept that there could be several directions, and you might have read books about 4-dimensional beings and 5-dimensional being and so on. So use your imagination, but assuming we have p dimensions here, then you could, by extension we could construct a length which is like x1, you have a vector with p dimension x1, x2, x3 up to xp, then its norm will be x1 squared plus x2 squared plus up to xp squared. So the 2 norm of a vector is nothing but its length if it is represented in a Euclidean space. So that is, with this my fear was out, and then I could deal with things. Any questions on this? See, if you do not have a question, I have a question. What is the 2 norm of a matrix? We will come to that. Huh? Matrix. Let us say square matrix. Hmm?
Heat transfer.
Norm will be some number. Norm is like GPA, one thing to distill everything that you are into 8.8 or 9.3 or whatever. Okay, so we will continue. For our vector space with Galerkin modes, so we construct a space with our Galerkin modes. Do we remember Galerkin mode eta eta dot? Yeah, everybody remembers? Yeah? No? You remember? Okay. Sir? Okay, cool. So we can think of it is like eta 1 cos kx plus eta 1 dot I mean the velocities were like eta 1 velocities were like cos or sine. Just check, I don't want to make a mistake. Yeah, pressure was like sine, so velocities were like cos, so it was like velocity was like eta 1 cos pi x plus eta 2 cos 2 pi x plus eta 3 cos 3 pi x. So this cos pi x cos 2 pi x cos 3 pi x, they are the basis function, they are like this ijk in our vector space, okay, and similarly eta 1 dot over k1, that is like the coefficient of sin j pi x, they are also the basis functions. So these things are like the individual vectors. So you have you write the coefficients eta 1 dot over k1, eta 2 dot over k2 ta, 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 up to eta n dot over kn. You can write it horizontally and put a transpose instead of writing a vector safe space. So if you take the norm, it will be eta I squared plus eta I over ki squared, right, summation over all the modes. So that is the norm of our vector space with covering this Galerkin modes. Is that clear? Yeah. So acoustic energy, it is a non-dimensional one, and of course when you non-dimensionalize, you can non-dimensionalize with different constants, so the expression you see in papers will change little bit, but it goes like p prime squared plus u prime squared scaled by some factors. Now the thing is, this norm is like a constant times the energy, which is what we need. If you scale it some other way, you would not get it proportional to energy. So we have to scale it that way such that the norm is like proportional to energy, then only the measure makes sense, because we are looking at the energy of the system, right. See, I mean when they scale the GPS, they multiply the theory courses by 4 credit and lab courses by 2 credit or something like that. So the idea is that the other thing is you put more effort, so you have to scale the grade more and scale the other one less or something like that. So you have to scale such that you get what you want, but a guy may be extremely good at laboratory but may be very poor at passing exams, so this scaling will not reflect his skills. But there if you weigh his lab thing by 10 credit and theory by 1 credit, he will come out on top. So what you get is what you give in norm. So there is no perfect answer to what norm you should use. In this problem it is kind of obvious use acoustic energy, but it is not at all that obvious for many complicated problems, but the basic thing is what you get is what you give is what you get or something like that, what you make is what you get. But in this case the 2 norm for state vector represents the acoustic energy. I hope this is clear. Acoustic energy goes like pressure squared plus velocity squared. So I got the slides from Peter Schmidt, who has given me permission to use them. So if you can write this formally as if Q is the it is a nice thing because sometimes some history is good, from some stalwart has written it. So dq over dt is LQ. So if it is a ordinary differential equation, how do you what is the solution? It will be like e power LT times Q naught. The same solution works for matrix. So you can write e power LT where L is a matrix times Q naught. So the question is, what is meant by matrix exponential? I think many of you know this, but I will do this formally here because some people ask me. So we look at exponential of a matrix. So we know the expansion e power x equal to sigma k equal to 0 to infinity x power k over k factorial, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus. So now let us construct this for a matrix. So let us say, so assuming that if we can follow the definition, as long as we can calculate x squared, x cubed, x power 4, then we can actually construct the exponential, because you can make all these powers then add up and construct this exponential of a matrix, right. So as long as we can solve the power. So if A equal to lambda 0 0 mu, then A power k would be equal to lambda power k 0 0 mu power k. This you can multiply it out and see it, and then or prove by induction or whichever way you want. So now the issue is, so then if you have this, then you can simply add up all these things, there is no problem. But the issue is, what if B is non-diagonal? Okay. So let us say B is non-diagonal. So but then you can say, we can always make this transform, what is this called? It's transformation? Huh? Similarity transformation, right. So how do you find this? How do you get the similarity?
It converts the matrix into either an upper triangular or a lower triangular.
So you look for the eigenvalues, right, and then you can calculate the similarity from the eigenvalue and the eigenvector. So so you can expand out with this, you substitute this for this, and then you can expand out this way, and now it is quite simple. So this will become 1 plus T inverse AT plus, what would this become? Again it will become T inverse A squared T plus, what would this become? T and T inverse will go, T and T inverse will go, so it will become A times A. So it will again be T inverse A cubed T plus T inverse A power k T plus blah, blah, blah. So one can be written as like T inverse T. So T inverse I T, right, I is 1 1 1. So this can be recast as T inverse times 1 plus A squared over 2 factorial plus, thank you, A cubed by 3 factorial T inverse. So this would be equal to T inverse e power A times T, okay. So this would be, make things formal, yeah.
You can only write this when the eigenvectors are linearly independent, because T inverse will only exist if the eigenvectors are linearly independent.
Okay. As long as you can find as long as you can do this decomposition, we can do this. Okay. But you are saying that if you are repeated eigenvalues, you cannot do this? Why?
Repeated eigenvectors, as in the eigenvectors.
Then why won't it exist?
Because then the matrix will be singular, the eigenvector matrix.
Two determinant matrix. Okay. Yeah, fine. But in okay, so as long as you can get this transform, then you can do this. So, so we want to look at energy at time, some time divided by energy at some time t equal to 0, and that would go like norm of this e power t times L, but L is the linear operator here, okay. So now this comes back to my question as to how do you get the norm of the matrix. Okay, so before that, so in summary, so we want to find in our notation norm of chi at t divided by norm of chi at 0, I mean squared. So you can define norm as square or without square. So this is the way I think I have seen it used by physicists. So they put if you have to put square, then norm squared is like energy. But the other people they sometimes you do not put square, so just have to be consistent with the notation. So what we need to find out is the greatest possible energy growth at time t, and we should be able to optimize it over all initial perturbations. So you have perturbations along various directions as you pointed out. Considering all the perturbations available, which one gives the maximum growth? That is the idea. So we want to maximize that. So you want to optimize over the initial condition and find this energy ratio or the ratio of the norms, and then we have to optimize it for all times, and then you can get the maximum possible transient growth. Is that clear? So you have to at each time you have to maximize it over all initial conditions, and then so these maximas you maximize it over all times, pick the one which gives the maximum over all times, that is the maximum possible transient growth, and the corresponding initial condition is the one that gives the maximum transient growth, okay. Now how do you do this? That is the idea. Would you have to integrate along, take all possible initial condition and try to integrate? Is that what you should do, or is there something available in linear algebra which you can use to address this? That is the next question. So we go back again, just to recap, dk by dt is L chi, so chi of t is e power minus Lt times chi of 0. So I bring this L to the other side, it becomes minus L chi. So we need the 2 norm of this matrix e power minus Lt, that is the crux of the matter. The 2 norm of any matrix is its principal singular value, that is the way it is defined, okay. Now there is a reason why it is defined that way, which you will see now. I mean people were smart in defining this way. So we need to do singular value of a matrix A. So I wonder if you know what is singular value decomposition. Do you know? No, okay. So if you have any matrix A, we can write this as U sigma V transpose. Now so what is the big deal about this? U is a unitary matrix, V transpose, which is the transpose of V, it is also a unitary matrix, and sigma is the matrix with non-negative numbers on its diagonal and zeros off diagonal, okay. So in principle if you have a matrix A, we can rewrite it as U sigma V transpose. Now how to do that I will explain afterwards, okay. I mean how to practically calculate these sigmas, but let us assume that we can do this, is that okay? So the idea here is that let us attempt to do a singular value decomposition of our evolution operator. So back to our differential equation, dk by dt plus L chi 0, and just to remind that this is the state vector eta 1 and eta 1 over eta dots and eta dot over j pi's, that vector, and solution is chi t is e power minus Lt times chi naught, and so we have to do SVD of e power minus Lt. So chi t is, so we replace e power minus Lt with U sigma V transpose, okay, assuming we have e power Lt minus Lt and we do SVD and you get U sigma V transpose, and we have just put it back, that is all, nothing more than that, just replaced e power minus Lt with U sigma V transpose in this equation, that is all, okay. But this has a profound physical meaning which answers the question Vikram asked. So let us see what this means. I have just rewritten this. So V transpose chi naught actually resolves the initial condition vector into a orthonormal basis of input vectors. We saw that V transpose is a unitary matrix. So this actually resolves the initial condition vector into orthonormal basis of input vectors, and the whole thing in represented in terms of u times something, it represents the output vector as a linear superposition of components along the orthonormal basis formed by the output vectors. Okay. So we multiply the matrix from right with V. Okay, we have e power minus LT as u sigma V transpose, and when you multiply a matrix with something, see when you multiply 1 with 2 you can have 1 first or 2 first, does not matter, but in a matrix you have to multiply either from the left or from the right, and both can give different answers and they will give same answer only under very special conditions. So here I am emphasizing that I am multiplying from the right side. So when I multiply this V transpose with V, what happens? It becomes identity. So I have e power minus LT times V is u sigma V transpose V, which is u sigma, because V transpose is unitary. So if you take the evolution operator and it acts on V1, which is this column, one of the columns of the eigen of the singular vectors. So this is the most, so e power LT when it acts on the most sensitive input direction will give sigma 1 is the maximum possible gain, and the direction will be u1 will be the most sensitive output directions. So this would be the interpretation where sigma 1 is the principal singular value. So singular values when they are returned in the descending order. The highest one will come first, the next highest will be next, the next highest will be next, and so on. So the top one is the principal singular value, and that is the one with the maximum magnitude. So this is the machinery in linear algebra available. So when you study linear algebra, it is just operations, but it is set up such that or I do not know who set it up which first, but it has a physical meaning in terms of studying energy growth. We can use that machinery here. The only critical thing is your norm should mean something physical that you care. So let us look at in terms of this matrices. So A is acting on V, and V consists of various columns. So let us take the first column, okay, that is corresponding to this one V1 here. Now this is equal to u1 times sigma 1. So this is how it will look in a matrix. Is that clear? So in a matrix structure, this line actually means the first column. So here it will return the first column and you have to multiply it by this. That is the meaning of this equation. Okay. So we are doing, again I must acknowledge Peter Schmidt for giving this nice illustration to me and giving me permission to use this. So you take SVD of e power LT, which you write as u sigma V transpose, or H here means Hermitian conjugate but same as transpose. So e power LT acts on this operates on V1 and you will get u1 times norm of the e power LT. Okay. So that is the amplification. This is the same as what I wrote, but you can see it kind of pictorially in terms of the columns of the matrix. And sorry, this this line actually means this is the one which is non-negative and everything else is 0 in this matrix. Yeah. So e power LT operates on input, then you get amplification times e power output. So you have this operator and these are the different directions that are available. So we have discretized the system in some sense. So actually infinite dimensional system we are discretized into this eta 1, eta dots and etas and so on. So you have finite number. So there are finite number of directions, but this when you do the SVD, this is the optimum initial condition, it is the left principal singular vector, and that would be the gain times the optimal final direction is the right principal singular vector. So the evolution operator operates on the left principal singular vector, it will give the right principal singular vector times the gain. Okay, clear? So principal singular value in effect gives the maximum energy amplification, and the corresponding right singular vector is the most sensitive initial condition. So let us look at G max is infinity, that means energy is amplified to infinity. When does it happen? That happens for classical linear instability. G max is 1, that means you had the maximum energy at time t equals 0, ever since then it is decaying. So that is classical stability. I mean you have eigen, let us say you have excitation along eigen mode and it just decays, and that is fine. G max greater than 1 but finite, so this is transient growth. So even a n tau model of Croco, we have done some calculation, and this is like in the parametric space we have plotted versus flame location versus n, and you can see the scale to read. Complete white is G max is infinity, complete black is G max is 1. So these pitch white portions are linearly unstable region, complete dark is linearly stable, and in between there is grey which is regions of transient growth. Same here, in this region there is linear instability, in this region it is classical stability, and in between there is a region where there is transient growth. So the regions of stability, instability and potential instability. Huh? Yeah, so you have regions here in which so what I have plotted is contour maps of G max. So when G max is 1, that means there is no growth or anything, so that is this region, and of course I cannot show infinite grey scale, human beings cannot see it and I do not know how to represent it. So up to 6 I have grey, but after that I have put white, which means and white corresponds to infinity. So if you use this model, you know we have done this already, there are regions where this is linearly unstable. So this complete white denotes linearly unstable region here also, and complete dark denotes classical linear stability, and in between there are shades of grey which would actually mean there are finite G max, like G max of 4, 5 and all that for this model. For some other model you may have larger or smaller. So so I can call this as regions of stability, instability and potential instability perhaps. So now location of the flame, XF.
Shouldn't that it should be some skewed kind of?
Yeah, so it not only the amount of acoustic driving depends on the n and tau or the heat release rate, but see Q is a function of U, but then U and P are also related, and what you want is the phase between Q and P. Okay, so
I was asking is some particular X values.
Just a second.
Even if low in
Yeah, right. So let me explain this. So we want P prime Q prime. So Q prime is, let us say goes like U prime times G. So it just doesn't depend only on G, but it also depends on the phase between P prime and U prime, or if it depends on the phase between P prime and U prime, the amount of driving. So this critically affects this. So that's the reason why XF is an important parameter. So it's not just n being large or small, but what is the phase between pressure and velocity, and then velocity and its gain when the heat gain of the heat release.
So shouldn't it whatever asking is, shouldn't it be, there should be some x values where even at low n
Yeah.
it goes to instability.
Yeah, it's possible.
So, but it's not.
Yeah, I mean, see, this is like a gray is increasing, right? I mean, so I mean, it is not like flat contours. Yeah, it's in a very complex shape. I can't really interpret, but yeah, it's possible, very much possible. So the I just want to stop with explaining how to obtain singular values, how to compute singular values. So A transpose would be U sigma V transpose transpose. This would be U sigma transpose, no, V transpose transpose, which is V times U sigma transpose. This is equal to V sigma transpose U transpose. Is that right? I should probably write transpose. So let us take A transpose, this is U sigma V transpose multiplied by V sigma transpose U transpose. So what is this? Yeah, so this would be U sigma transpose U transpose. So this can be rewritten as U transpose inverse sigma transpose U transpose. So what transformation is this of A transpose is this? That is a similarity transform. So that means this is the, this will contain the eigen values of A transpose. So if it is a square matrix, sigma square will contain eigen values of A transpose. So the way to get singular values of a matrix A is to multiply it by its transpose and obtain the eigen values. That will give the square of the singular values. Very simple. And if you are using MATLAB, you can have just commands to do all this. Okay, I am out of time, so I'll stop here. So we looked at the evolution of the operator, and we looked at the linear evolution of a dynamical system, and we saw there was an analytical solution, and then we tried SVD, and then we found that we could find the optimal initial condition and the maximum energy amplification using SVD. So we will stop here next.